Good afternoon, class. Today we're going to be discussing inverse functions, and I want to remind you about the definition of function. Remember that a function is just any set of ordered pairs where there's no repeated x value. Question? I'm not right. I'm just talking at this. Oh, yeah.
Oh, go ahead.
Thanks for doing that. Thanks for telling me. I'm not writing anything yet, but let's consider a couple of functions. I'll call this function f. And let's say it has the ordered pairs 0, 9, -1, -3, and 7, 4. That's an example of a function. Notice a function we said it can't have repeated x values. Notice every one of these x values is unique. 0, -1, and 7. Here's another example of a function. I'll call it g. Let's say oh, this pen is not good. And let's say notice both of these are functions. Notice each one has different x values. Notice 2, 4, -2, different x values. So both of these sets of ordered pairs of functions. Let's suppose we reversed the ordered pairs. If we reverse the ordered pairs, so 0, 9 becomes the ordered pair 9, 0, then that's what we call an inverse. To indicate an inverse function, that the ordered pairs are being reversed, we use a little superscript of -1. That's not saying f to the -1 power. That's not saying the reciprocal of f. If you see a function with a superscript of -1, that's our lazy way of saying the inverse of f. And that means we're switching the ordered pairs. 0, 9 becomes 9, 0. -1, -3 becomes -3, -1. And 7, 4 becomes 4, 7. What about the inverse of g? G inverse.
4, 2.
Okay, 2, 4 becomes 4, 2. -2, 4. I agree. We're just reversing the ordered pairs and 4, -2. We started off with two functions, f and g. We created their inverses. I claim one of those inverses is not a function. Even though the original expression was a function, one of these inverses is not a function. Now, I agree. Look at g. Remember we said a function can't have repeated x's. Right there. We have 4 being assigned to 2 and 4 being assigned to -2. What went wrong? Why did this happen? F and g are both functions. They had no repeated x values. But when we formed their inverses, one of them is a function, one is not a function. What went wrong? How do we pick up repeated x values? How do we pick up repeated x values here on this g inverse? Why do we have repeated x values? Where do those x values start off? As y values. It's perfectly fine to have repeated y values. Notice g had repeated y values. F didn't have repeated x values or repeated y values. That's the problem. If you have repeated y values in the original function, when those y's are going to become x's, and as a result, the inverse will not be a function. If there's no repeated y values, we say the function is 1-to-1. No repeated y values, We say the function is 1 to 1. So f is 1 to 1. Notice there's no repeated y's. F is 1 to 1 is 1 to 1. Whereas G is not 1 to 1. We have those repeated y's. When we flip the ordered pairs, they become repeated x's. Not 1 to 1. 1-to-1 functions are important because only 1-to-1 functions have inverses that are functions. If a function is at 1-to-1, you can still find the inverse. It's just not going to be a function. So I'm going to say, note, this is an important note, only 1-to-1 functions have inverses that are functions. Any questions up to this point? No? Well, I'm going to make another observation, and that's related to domains and ranges. With the domain of a function is the set of all x values. The range is the set of all y values. If we look at the domain of f, the x's in the original function, the x's in the original functions, once you form the inverse, what do those x's become? The x values in the original functions, what do they become? The y values. So the set of y values is the range. So the domain of f is equal to the range of f inverse. What about the range of f? Apply that same logic to the range of f. The y's in the original function, what are they going to become in terms of the inverse? The domain. The y's in the original become the domain in the inverse. And there will be some questions regarding that concept in the homework. I think I've talked enough for a while. How about doing some homework? Tony assures me students hate it when I do all these examples that aren't in the homework. So let's go on to the homework. Let's see there. There. We haven't even, that's not the one I want to discuss. Let's see, is it number 4? I'm looking. I thought it was number, it's here somewhere. Is that it? Yes. Just, are these functions inverses? There are some questions here that just, you can just look at them and answer very quickly. Okay, if they're inverses, the ordered pairs have to be reversed. -3, -6, yeah, that's right. 0, 4, and 4, 0, yes. 4, -3, when we reversed that ordered pair, it became -3, 4. And 6, 9 became 9, 6. I agree with Jacob, yes. So there are some short questions, fast questions. What about number 5? If this function defines a 1-to-1 function, then they want us to find the inverse. If it's not 1-to-1, they want us to select not 1-to-1. Let me see. First of all, we may as well confirm that it's 1-to-1. 1-to-1 means there's no repeated y values. What do y'all think? Is it 1-to-1?
Yes.
Yes. So let me write this problem down. We're going to have to find the inverse. The ordered pairs are negative 19, comma, negative 14, and 4, comma, 20, and negative 11, 19. So let me switch it over here to my, what I'm writing there. Let me move this out of the way. There. Okay, let's find the inverse. I'll find the inverse in blue.
Negative 14, negative 19.
Okay, so we're just reversing x and y, so negative 14, comma, negative 19.
24.
Okay. And
19, negative 11.
okay. I imagine most of y'all would have just looked at the ordered pairs and flipped them there without writing down this stuff, but I just felt like I should write down something for this problem. So 14, negative 19, 20, is it B? 24, 19, comma, negative 11? Yeah. Okay. There, and check it. So, any questions there? Let's switch back. I got to talk some more now. Remember, there was another way of expressing functions. We can express them using a graph. And recall for a function, we had something called the vertical line test. Let's see. There. Okay. Recall the vertical line test. The vertical line test. It said that if you have a graph of some expression and you're wondering, is that thing a function? If you can draw a vertical line so that it passes through this graph in more than one spot, 2 or more spots, the thing isn't a function. So what do y'all think here? Is this a function?
Yes.
Yes, it doesn't matter where you draw that vertical line, you're not going to hit it in more than one spot. So this black graph that I drew, it's a parabola opening downward, it is a function.
It doesn't have repeating x values. It's a function.
That's correct. There's no repeating x values. I'm going to write that down. No repeating x values. However, I claim this thing is not one-to-one. I believe there are repeated y values. Look right here. Oh, how is it? Look where this black graph is passing through the x-axis. Right there and right there. This number here, the x value, has to be positive because we're moving to the right of the y-axis. So it has a positive x value, but the y value is 0. Look over here. We have a negative x value, but what's the y value? At this point here, what would it be? It's the x value is negative, the y value is still 0. We have repeated y values, so this graph is not one-to-one. It's not one-to-one, and that is repeated y values. If you can draw, it doesn't have to be the x-axis. If you can draw any sort, a horizontal line so that it hits the graph in 2 or more spots, it is not one-to-one. For example, If I drew, let's say that line right there, it hits it in two spots, it's not 1-to-1. We have the vertical line test to determine whether a graph represents a function. We have the horizontal line test to determine if the graph represents a 1-to-1 function. Well, if it's a function, it has to pass that vertical line test. But for the horizontal line test, I'll write it like this. If you can draw a horizontal line that hits the graph, if you could draw a horizontal line, thank you, Tony, that hits the graph in two or more spots, then the graph is not 1-to-1. So let's look at, before we do, here's one that I remember Dr. Barton that always would put this on his college algebra test. Okay, and then he'd have such a good laugh. The question is this a 1-to-1 function? Here it goes.
Yes. No.
It's one of those, you're right. Is this a 1-to-1 function?
It is, no, it's not, because it passes the y twice.
Okay, it's not a function. That's right. It is 1-to-1. You can try drawing those horizontal lines all you want. You're not going to. Yeah. You see, there are plenty. I mean, the horizontal line isn't going to hit it more than once. But the vertical line test, this thing is not a function. Oh. But let's look at don't bother writing that down. Let's look at the examples in the homework. Number 1. This is one of those. Can you blow up the graph? Let me do it.
Yes, it is 1-to-1.
And this is actually answering the question, is a slanted line? Slanted lines are functions. Are they 1-to-1?
Yes.
Yes. All slanted lines are 1-to-1 functions. I'm going to write that down.
Okay, but I'm going to, okay, I'll show.
Okay. Oh, did you select,
I haven't checked it.
yeah, let's check it. Okay. Oh, let's see. Use the horizontal line test to determine whether f is 1-to-1. Try blowing it up like that.
Is.
Do you try drawing?
But it's already horizontal lines.
Oh yeah, there are. There are already horizontal lines drawn there. You're right. And so it's a function. It passes the vertical line test, but it passes the horizontal line test also. So this is a 1-to-1 function.
Now, right here you might think, wait a minute, it looks like it's about to turn around. If it actually turned around, it wouldn't be 1-to-1, but it doesn't show it turning around.
It's just going to keep on decreasing very slowly. Don't make the assumption it's going to turn around.
I remember one semester a student, told me she thinks it's going to turn around, and that's why she wrote no. And I was like, don't think, just look at the little graph right out here.
Don't record that.
Yeah,
Tell the student don't think.
No, I don't. Don't assume something that you don't see. You don't see it turning around. It would be better, I think, if the graph had just started right out here and went, rather than right here where it starts looking like it's about to turn around. Okay, but what is the answer to this? Is it 1 to 1?
Yes.
Yes. So far, these questions are pretty fast. Okay, so
Pretty easy. I can't wait for question number
Inverse?
6, and it's impossible.
oh, I don't think so. What's number 3? Oh, here's some more just finding determinant whether these functions are inverses, and I think this is something that we can do without showing any work.
No, they're not.
They're not.
No, because there's 4, 1, and
Okay.
Okay, yeah.
Yeah, there it is. Okay, notice 2, 5. 2, 5, it was reversed to become 5, 2. 1, negative 2, reversed to negative 2, 1. But 4, 1, if it was going to be an inverse, it should be 1, 4, not negative 1. So pay attention. Watch closely. No, first glance, I was thinking it was they weren't inverses. And number,
Done 4 and 5.
I know,
6.
number 6. Oh, okay, it's another one. My goodness, this is a quick assignment, maybe.
It's
Oh,
6.
yeah.
You have to see.
It's C. Well, first of all, is it 1 to 1? If the following defines a 1 to 1 function, find its inverse.
Oh, it's not 1.
It is not 1 to 1. Be careful. We have repeated y values. Negative 3 is assigned to 17, and positive 2 is also assigned to 17. You have repeated y values, so this thing is not 1 to
I
1.
just tried to find its inverse. When C is the inverse, but it's not 1.
It is not 1 to 1. And generally, if it's not 1 to 1, they're not going to want you to find the inverse. An inverse exists, but it's not a function, so they're not going to want you to find it.
What's the common wrong answer here?
I think it's C. They reverse 17, negative 3, 2, 17, 17, 2. I think the common mistake is response C.
But I remember once having a question like this on a test, and every student missed it. I was like, oh, wow, what problem is this that every student in the class missed? And it was that, okay? And then I think I decided to solve that problem by removing it from a test.
But that's not saying it won't be on y'all's test now, okay?
Yeah, that was like 10 years
I
ago.
would have gone in there and I would have said, Tony, what are you doing? Don't you dare. In case you haven't figured out, he's the nice one.
Oh.
He's the nice one. Y'all over there, y'all are stuck with the mean one. I'm just in a good mood today because my cancer results came back. Still nothing detected. So, yeah. Yeah. So, oh, goodness. I like this assignment. Everything's so
The
fast.
answer is B.
Well, okay, let's make sure it's 1 to 1. Negative, looking at the y values, negative 7, 63, negative 9, negative 6. It is 1 to 1. And so 2, negative 7, which one did you say it was?
B.
B, let's check. That's 7, 2. 10, 63 becomes 63, 10. This is looking good. 5, negative 9, negative 9, 5. Negative 9, negative 6, negative 6, negative 9. Yes, B, I agree. Okay. Oh, this goes back to something we were talking about earlier. This is something back when I was talking.
F is equal to the range of F inverse.
Okay.
The range of F is equal to domain of
Okay,
F.
God, that page, I didn't realize this page looked so messy until I look at it now. We're looking at this stuff right here.
The paper actually looks neat.
Oh, well, thank you, Jacob.
Whoa.
Okay, there. I'm going to throw that away. Okay, remember I said the domain of f, the x's in the original function become y, so the range in the new function, the range of f, the y's in the original become x's in the new function. So looking over here, the domain of f is equal to the
go.
Yeah, this is a little pull down menu, select range of F inverse, and the range of F is equal to the I agree. And then, of course, they give this wonderful little box here. Let's see. Consider that F is a set of ordered pair x, y, where x belongs in the domain and y belongs in the range. The inverse of a function F can be obtained by interchanging the x and y values. Note that F inverse is a set of ordered pairs yx, where y belongs to the domain and x belongs to the range. I think they're just trying to sound fancy here. You're just flipping the ordered pairs. I don't know why they have all that long exposition there. Oh, I like this one. Let me write it down. Okay. This is number 9. They tell us that F has an inverse and that F of -3, I'm writing it down, is equal to 6.
And that, the exact opposite of
what is defined F inverse. Okay. Oh goodness, I'm here writing it down as Jacob is telling us the answer. So let's see.
I asked at the beginning of the year if I could do that.
Okay, well, F of -3 is equal to 6. And remember the ordered pair representation. That's saying that when x is -3, the y value is 6. So when you find the inverse, the x value would become 6 and the y value would be -3. So when x is 6, the y value is -3. It's another question. They're just trying to make sure you realize they're just reversing the x and y coordinates. Any questions on our logic there? So, -3.
Good job.
Okay, and then they give us all that little exposition. Okay, we need to talk about equations that are, functions that are written as equations. Remember, the most popular way of expressing a function, you can do it by listing ordered pairs. I call that the tabulation method. You can express a function by graphing it to show all the ordered pairs. The other method, I'll say how to represent a function well, let's see. You can just list ordered pairs. Or you can do it graphically. The third method, the most common method, of course, is through the use of a function equation. And we know what to look for. If we're trying to decide, is a function one-to-one, we know what to look for. For a set of ordered pairs, you want to make sure there's no repeated y values. So for one-to-one, if you're looking at a list of ordered pairs, you want no repeated y values. No repeated y values. If you're representing the function graphically, and you want it to be one-to-one, remember you have the horizontal line test. Now, if you're looking at a functional equation, what would make it not be one-to-one? What would create those repeated y values? What could we do? What could an equation have that would create y values? I mean, the same y values. I think it's those even exponents that cause problems. Remember, if you take a positive, whether it's positive or negative, when you square it, what sort of result do you get? A positive number. So if you had something like y equals x squared, if you plugged in -1, I think I'll say -2. -2 times -2 would give you 4. If you plug in +2, you'd still get a y value of 4. It's that squaring, the way that even exponents take negative quantities and change them to positive quantities. So if you're looking at a function equation, there's one thing you definitely need to be on the lookout for. Not 1-to-1. The equation would not be 1-to-1 if it has even exponents, x squares, x to the fourths, what have you. There's something else we saw, another function we saw this year, this semester, where we have negative stuff on the inside of it, but once we perform that function, whether it's negative or positive on the inside, the result turns out positive. What function was that? Had the shape of a V when we graphed it. Did you say absolute value? That's it. Absolute value. If your equation involves absolute value, it's not going to be 1-to-1. So, even exponents, not 1-to-1. Absolute value. So when you're looking at a functional equation, if you have even exponents, it's not 1-to-1. They won't ask you to find the inverse in that event. If you have absolute values appearing, it's not going to be 1-to-1. There was something we were doing at the end of the homework assignment involving composition of functions, and I said this is going to be important when we get to inverses. Here's our formal definition of inverse functions. We have that intuitive notion. We know that an inverse function reverses the x's and y's. But here's our algebraic definition of inverse function. Inverse function. Assume the two functions I'm about to use are 1-to-1, okay? Let's assume f and g are 1-to-1 functions. Assume f and g are 1-to-1 functions. F and g are inverses if each of the following is true. There are two conditions. Here they are. The first one, f composed with g of x reduces to x. Remember that little fog and gulf. F composed with g of x reduces to x for every x in the domain of g. And if you reverse the composition, g composed with f of x reduces to x for every x in the domain of f. And we had some problems when we were looking at composition, and I said it's trying to get you ready for this definition. This is saying if you perform the two functions consecutively in either order, you're going to end up wherever you started. That's what this algebraic definition is saying. To illustrate what I mean by that definition, I'm going to make up two 1-to-1 functions. Okay, hold on. Flip back. There. You see it? And while, let me look. Operations, difference quotient, and composition. That was it. It was the assignment over operations, difference quotients, and compositions. Okay, you got it? Hold on. Where is, I recall, let me find it. Okay. Like number 10. Here's a problem like the number 10 from that assignment. They gave us two functions, and they told us to find f composed with g of x. It reduced to x. We then went the other direction. It also reduced to x. And then they'd ask, are they equal? And yes, they were equal. Y'all remember doing those? And I said that they're trying to get you ready for this algebraic definition of inverse. There was one with a cube root. When you perform the two consecutively, both times, they reduce to x. And what this definition is saying, if you perform the two functions in either order, and you always end up where you start, then those functions are inverses. Consider, okay, 1, 2, and there's 3, 4. Let's suppose, if I were you, I wouldn't bother trying to draw this diagram. They're not going to have any of these diagrams in the homework, but I'm trying to make a point here. If assigns 1 to 3 and 2 to 4. Now, if G is the inverse, it would have to assign 3 back to 1, and 4 would have to go back to 2. That formal definition is saying it doesn't matter where you start. If you perform the two functions consecutively and you always end up where you started, the only way that's going to happen is if the ordered pairs are being reversed. So if you start here at 2, 2 goes to 4, 4 goes back to 2. Let's say you start there at 3. 3 goes to 1, 1 goes back to 3. You end up where you started, and the only way that happens is if the ordered pairs are just reversed. So these are inverses. And one more. With our intuitive notion of, let's say, 1 goes to 3, 2 goes to 4, there's F. Suppose G took 3 to 2 and 4 to 1. So the green is the G function. If you perform this function, these two functions consecutively, you're going to end up where you started. 1 goes to 3, but where does 3 go? 3 goes to 2. You're not ending where you started. That means these things are not inverses. Any questions? Okay, now we better do something like what's in your homework. I think it's number 10. They want us to determine whether the two given functions are inverses of one another. For one thing, when I look at those functions, are they, the first question I asked myself, are they one-to-one? What did I say? An equation? What are you on the lookout for? What creates those repeated y values?
If they have a repeated
value. I think I should say be more general. Or maybe I should say be more specific.
Well, the first one doesn't have like anything. It's just like
the two things you want to avoid: even exponents, absolute values. Did the equations contain absolute values? I think that's a real fast thing. A question there. Are there any absolute values there in f and g? No, remember absolute values have those big bars, so there are no absolute values. What about even exponents? No, so these are one-to-one functions. If that denominator on that f, if it had been a 2 over x squared minus 9, they would not have been one-to-one. So, looking at number 10, let me write the two functions down. We have f of x equals a 2 over x minus 9, and g of x is equal to 2 over x. The fraction is 2 over x, but the plus 9 is stuck outside. They want us to decide whether these functions are inverses. Well, let's find their compositions. If their compositions both reduce to x, then they are inverses. Now, if their compositions don't reduce to x, then they're not inverses. Let's find them. F composed with g. Here goes the first one. F composed with g of x. Switch it over for me. There. F is on the outside. On the inside, we have g of x. G of x, we know that. That's 2 over x plus 9. So now we want f of 2x plus 9. So we're taking 2 over x, plus 9. So we take this step here, we go up here and replace it with that x. So we're going to have, this is getting a little messy, 2 over, we have that circled stuff, 2 over x plus 9. And we still have something else stuck on there in the bottom. What is it? We replace the x with 2 over x plus 9, but we still have that minus 9.
But wait, because it's under the denominator, or it's at the denominator, what? Oh, okay.
9 minus 9, I think we'll all agree that that cancels. That subtracts out, it's gone. And we have what's called a compound fraction. 2 over x. A fraction that contains one or more additional fractions is called a compound fraction. The method that I like to use to reduce a compound fraction is to multiply above and below by the minor denominator. Realize this is the major fraction bar. That long bar there, that's the major fraction bar. The minor denominator is the denominator of the resulting fraction we have. That denominator is an x. Let's multiply above and below by x. Tony, is that how you reduce these things? Yes? Then something very nice is going to happen. Look down here in the big denominator. X will cancel with x. So all we have, on top we have a 2x. What have we got on the bottom? Just a 2. Remember, if they're inverses, everything has to cancel out except for the x. Well, this way it did reduce to x.
If you're a gambler, there's about an 80% chance if one of them equals x, the other one's going to equal x.
If you're a gambler, then yeah, that's right. Odds favor. If one reduces to x, they'll both reduce to x. But is it guaranteed? No. The only way
we don't have to gamble now.
We don't have to. We're going to do the other one now. G composed with f of x.
But if you find yourself one of them equaling x and one of them not equaling x,
I'd go back and check my work, because if one composition reduces to x, odds favor the other one will also. So we have G composed with f of x. Now, this time, f of x is what's on the inside. So we'll put,
over x minus 9.
and then that says go to G, and where you see the variable right there, you're going to write in.
So it's 2 over 2 over x minus 9.
And we
Plus
still,
9.
and we have that plus 9 stuck on out there. This one isn't as easy to reduce. What's my minor denominator? X minus 9, we're going to have to multiply above and below by x minus 9. We'll multiply here by x minus 9, up here by x minus 9. The x minus 9's cancel. Remember, if they're going to be, if it's going to reduce to x, everything needs to cancel out except for that x. So I'm going to clean this up a little bit. We have that 2, and it's being multiplied by x minus 9. Resist the urge to start. I would not do that. Remember, you want to cancel out stuff, and if you're going to cancel stuff, it needs to be written as a product. If you distribute that 2, you're not going to be able to cancel that 2 right there. I think it's already written in the desired form. The 2's cancel out. So we have an x minus 9 plus 9. What's that about to reduce to? X. Both compositions reduce to x. So yes, F and G are inverses. Oh, hide that. Wait.
Technically A.
Well, so I'll write F and G
Oh, what? Let me show what you're on.
are inverses. Oh, move the little thing down.
Oh.
Since Any questions there? If you have two functions and you're wondering, are they inverses? Find their compositions. If they are, everything should cancel out except for x. Okay, number 11. Oh, did you punch in the answer that they are inverses?
Mm-hmm.
So we know when we have two functions, switch over here.
Oh.
No. Oh, well, okay. When we're wondering, are these two functions inverses? We know what to do. Find their compositions. So the natural question is, suppose you have a one-to-one function, how do you find its inverse? Look at number 11. That's still number 10. Determine whether the function is one-to-one. After what we've said here, this should be real fast. Is this function one-to-one? Yes. What could I do to make it not be one-to-one? I could do something to that x that Tony's pointing at. What could we do? If we changed it up, maybe put, in place of x, put what? Maybe an x squared? You put an x squared, whether you put a plug in a 2 or a negative 2, you're still going to get the same thing. So, but this is one-to-one. If it is one-to-one, they want us to find a formula for the inverse. So, switch back, I need to write out some steps. And these steps are very logical, and they're pretty short. It's not like the cut point method or completing the square. To find the inverse, of a one-to-one function. Maybe I should just say find the inverse of a function, and then maybe I should write that first step. Make sure it's one-to-one. No even exponents, no absolute values. I'm going to write that out. I'm going to write that. Make sure the function is one-to-one. That means no even exponents, no absolute values, and there are plenty of other functions that aren't one-to-one. like
The
the sine and cosine trig functions, but for our purposes, the things that aren't one-to-one involve even exponents and absolute values. So make sure you don't have those. Then now tell me in words the second step. The second step, how do you find an inverse? In general, what is an inverse function doing? Think about how we found those first inverses. Right when we started this class today, let's see, how were we finding these inverses? Okay, so I think what I'll say is we're flipping the x and the y. Oh, what do you think? Okay, switch the x, y, switch the x and y. So whatever's x becomes y, whatever's y becomes an x. At that point, you have an equation that represents the inverse, but they want you to write it in inverse function notation. So the third step will solve for y. And then the fourth step, replace y with the f inverse notation. But all of the work is right here. Switching the x and y and solving for y. Because once you solve for y, you won't have to type in this inverse function notation. They'll have f inverse of x equals and a box. So once you solve for y, you've got the inverse. So this is number 11. Let me write it down. We have the function f of x is equal to 2 over x plus 3. And we've already said, yes, it is one-to-one. There are no even exponents, no absolute values. So now they want us to find the inverse. We've made sure, okay, let's switch over. Okay, we've already made sure that it's one-to-one. We're going to switch the x and y. Wait a minute, I don't even see y here. What's taking the place of y? That f of x that's just a fancy way of saying y. So that y is going to become an x. That y becomes an x. And the x becomes a y. F of x is just a fancy way of saying y, so the y became the x became the y. Now we need to solve for y. We need to get the equation with the y by itself on one side. Well, if we're going to solve for y, we can't leave y down there in the denominator. So remember, whatever you do to one side of an equation, you have to do to the other side. So I'm going to multiply both sides by y plus 3. I'm going to multiply by y plus 3. That green is hard to see, isn't it? There. Something nice is about to happen over here on the right side. What is it? What's going to happen here? The y plus 3's are going to cancel out. So all you have on the right side is a 2. Well, how are we going to multiply y plus 3 by x? What are we going to have to do there? Distribute. You take x times y, that's xy, plus
3x.
X times 3 is 3x.
Minus 2 on both sides.
Well, we want the y by itself, so I think I'd leave this xy where it is. I think I'd move this thing over.
Divide by x on both sides.
No, I'm not going to divide by x yet. That division, when I'm solving for a variable, the division is the last thing I do. You could do that, but that's not how I'm going to do it. I have a 2. I'm going to move the 3x to the right to have me a 2 minus 3x. Any questions there? And then it's x times y. We need to get y by itself, so what can we do? Divide by x. I agree. So we're going to then have y equals, I'm moving it up, y equals 2 minus 3x all over x. So we switch to x and y, we solve for y. The last thing, replace y, get it back in terms of function notation. So replace y with f inverse of x. And that's not really required. You'll see why in a moment. The thing we're going to be typing in is 2 minus 3x all over x. But once you solve for y, you have the answer. That answer is right here. Once you've got it in the form y equals, the stuff on the other side is your answer. So this little 4-step process is really only a 3-step process. Once you've solved for y, you're through with the problem. Any questions? Okay. Fraction hot button. 2 minus 3x on top. 3x.
Ooh.
And on the bottom we have an x. Switch back to my work. Any questions on my logic here?
Oh, it looks so messy.
It looks terrible, I know. Oh. Well, maybe there's another one that I can do that'll look neater. Let's see. Number 12.
Last one.
Oh, yeah. What have we got added on at the end? Maybe some cut point problems. Same instruction. Is that my phone? Oh, goodness. I'm sorry about that. Determine whether a function is 1-to-1. If it is, find a formula for its inverse. While I'm writing this problem down, y'all decide if it's 1-to-1. F of x is equal to x cubed minus 5. Is this function 1-to-1? What do y'all think? It is? Well, I see an exponent, though.
No, it's not.
But it's an odd power, so realize odd exponents don't take negative numbers and change them to positives. Negative 2 times negative 2 times negative 2 is negative 8. It doesn't become, when you take a negative number and cube it, it stays negative. I'll say odd, so 1-to-1.
Oh, let me type that.
Okay.
Or not type it. Is it 1-to-1?
Yes. And now they want us to find the inverse. So let's look back at our steps. We've already confirmed that it's 1-to-1. We've already confirmed it's 1-to-1. We better switch the x's and y's. So remember, f of x is acting like what letter? That's y. So y becomes x becomes y. Oh, this is going to work out nicely. We switch the variables. That was step 2. Now we're going to solve for y. We need to get y by itself. What do you think we should do? I'm going to get that y cubed by itself first by adding 5. I agree. So that's an x plus 5 is equal to y cubed. Now, what are we going to do to get rid of that cube? What undoes a cube?
I heard someone say it.
I think I heard someone say it. A cube root, I agree. We're going to take the cube root of both sides. So the cube root of y cubed Those things just cancel out there, and we're left with just a y equals the cube root of x plus 5. I think this one was cleaner than the previous one. So the thing on the other side of y, I'm not even going to write it, but the F inverse notation, there's the answer that I'm looking for. The cube root with x plus 5 under the radical. Have we typed in any cube roots this semester? I don't think so. So click over there in the box. Question? Go. Okay. The radicals we've typed in this semester, I think, are square roots, and there's a special square root hot button. But for the cube root, we're going to have to use the nth root hot button. Okay, so we click there. Look at the two hot buttons involving radicals. There's the square root. We'll click in there. There's the square root. That's not what we want. If you have a root other than a square, use the nth root hot button. And notice the first thing you have to do is type that little index. What are we going to type up there? Well, a 3 because it's a cube root. And what have we got underneath the radical?
X plus 5.
Mm-hmm. Yes. Any questions there? And I think starting at number 13, it is review. It is.
Yeah, circle.
Oh, a circle. That's good. Y'all need to practice that. And of course, cut points. And more cut points. Okay. Oh, well, any questions? Pretty easy as these things go. This was one of the less rigorous assignments.
And one of your shorter videos, too.
I know, I am long-winded. Go ahead and stop it.